Have you ever really stopped to think about what's happening when you stretch a rubber band? It feels simple, but it's all about this incredible hidden property of matter called elasticity. And it's not just in rubber bands. It's the invisible force that governs how buildings stand, how bridges flex, and, why some things bounce while others just kind of splat. Okay, let's get right into it.
Right, so it really all boils down to this simple question. A rubber band snaps right back to its original shape, but if you take a piece of clay or some silly putty and stretch it out, it just stays that way. They're both solid materials, so what's the fundamental difference in how they react to being pulled? That is the core idea we're going to unpack today.
So here's our game plan. First, we're going to define the two basic ways materials can behave. Then, we'll look at the cause and effect of deforming something, that's stress and strain. After that, we'll get to the simple, golden rule that connects them. And finally, we'll see how we can actually give every material its own stiffness score.
All right, first things first. Let's establish the two opposing teams in the world of materials. You've got the ones that bounce back and the ones that, well, don't.
So, on one side, we have elasticity. This is just a material's ability to return to its original shape and size once you stop pulling or pushing on it, like a spring. On the other side is plasticity. This is when a material decides it likes its new deformed shape and just stays that way. That piece of clay we were talking about, that's a permanent plastic change.
Now you can see some great examples of the extremes right here. On the left, you've got materials like quartz and phosphor bronze, which are considered almost perfectly elastic. They snap back with incredible precision. And on the right, you see perfectly plastic materials, like wet clay or wax. Once you squish them, they stay squished. The thing is, most materials we deal with every day are somewhere in the middle of these two extremes.
Okay, so what actually causes an object to change its shape? It's not just the external push or pull you're applying. It's really about the internal forces that build up inside that material. And this internal resistance has a name. It's called stress.
So here's the key thing to remember. Stress isn't just the force. It's that force spread out over a specific area. See how the definition mentions both a deforming and a restoring force? The deforming force is what you're doing from the outside, but the restoring force is the material fighting back on the inside, trying to keep its atoms together. That's exactly why a sharp knife cuts so well. It concentrates all that force onto a tiny, tiny area, creating this immense stress that the material just can't handle. Now, stress comes in a few different flavors. The most common one is called normal stress. This is what's happening when you pull something apart. That's called tensile stress, or when you squeeze it together, which we call compressive stress. The force is acting straight on, perpendicular to the surface. And this shows it perfectly. You can see those forces marked with an F pulling directly outward on the ends of this cylinder. The material inside is feeling that tensile normal stress as it resists being ripped apart. Next up, we've got bulk stress. The best way to picture this is to imagine taking an object and dropping it deep into the ocean. The water pressure pushes on it evenly from every single direction. That uniform all-around squeezing is what creates bulk stress. And this illustration is showing exactly that. The forces are pressing inward on the entire surface of the object. This kind of stress doesn't really try to change the object's shape, but it does try to change its overall volume. It's trying to make the whole thing smaller.
And finally, there's shear stress. Now this one's a little different. Instead of a direct push or pull, the force is applied sideways or tangentially. A great way to think about it is pushing the top cover of a thick book to the side while you hold the bottom completely still. The book changes its shape, right? But it doesn't get bigger or smaller.
And here you see it in action. The bottom of this block is fixed in place, and there's a force F pushing the top surface sideways. That causes the block to lean over and change its shape, but not its size. That is a classic example of shear.
Okay, so stress is the cause, that internal force. So now let's look at the effect. How do we actually measure the physical change, the deformation that we can see and feel? Well, that's where strain comes into the picture.
The absolutely crucial thing about strain is that it's a relative measurement. It's not just about, say, how much longer a rubber band gets. It's about how much longer it gets compared to how long it was in the first place. You take the change and divide it by the original. And because of that, strain actually has no units. It's just a pure number, a ratio.
And just like stress, strain comes in three types that match up perfectly. Normal stress causes a longitudinal strain, that's a change in length. Bulk stress causes a volumetric strain, a change in volume. And you guessed it, shear stress causes a shear strain,
a change in the object's shape, which we actually measure as an angle. It's a perfect pairing of cause and effect.
So we have our cause, stress, and we have our effect, strain. But how are these two things actually related? Is there any kind of predictable connection? Well, it turns out, for most materials, there is a simple, really beautiful rule.
This really is the million-dollar question. If I apply a certain amount of stress to something, can I predict exactly how much strain I'm going to get? For a long, long time, the answer has been yes, and it's all thanks to a brilliant 17th century scientist named Robert Hooke.
He figured out this whole relationship using an experiment that looked just like this one. He'd hang a spring, measure its length, then he'd add a weight to that little pan and carefully measure how much it stretched. Then he'd add another weight and measure it again. He just did this over and over, meticulously reporting everything he saw.
And this is what he found. This right here is Hooke's law. What it says is that as long as you don't stretch something so far that it's permanently damaged, that's what the elastic limit means, the amount of stress you apply is directly proportional to the amount of strain you get. So, if you double the stress, you get double the strain. It's as simple as that.
And here is the beautiful result of Hooke's hard work. When he plotted all his data with the load, or the stress, on the vertical axis and the amount it stretched, the strain, on the horizontal, he got a perfect straight line going right through the middle. This graph is the visual proof of that direct proportional relationship.
Okay, so stress is proportional to strain. That relationship is more than just a cool fact. It gives us an incredibly useful tool. It gives us a way to assign a single number to any material that tells us exactly how stiff it is.
And that number is called the modulus of elasticity. It's simply the ratio of stress to strain. As you can see in this table, there's a specific modulus for each type of deformation: Young's modulus for stretching, bulk modulus for compressing, and shear modulus for changing shape. And this is why it all matters. If you're an engineer designing a bridge, knowing this exact number for steel is everything. It tells you precisely how much a beam will bend under a certain load. A material with a high modulus, like steel, is super stiff. One with a low modulus, like rubber, is super flexible.
So this elegant dance between stress and strain is happening all around us, all the time. It's what keeps our world from falling apart. But every single material, from a skyscraper cable to a bone in your body, has a breaking point, an elastic limit. And it makes you wonder what is actually happening down at the atomic level in that exact moment when something stops stretching and just starts to snap.